Dr. Atchison again, and we're still talking about Chapter 7, Perception for Motion and Perceived Action. This is our third video lecture where we're going to be talking about eye movements and how those influence our perception of both moving objects and still objects. So there's different kinds of movements. The first one we're going to talk about is saccades. So these are those rapid eye movements, kind of the back and forth. Kind of think of it as like you're watching a tennis match. The eyes go back and forth. These are called saccades. Another kind of movement is called smooth pursuit, also called tracking. So if you're watching a car drive down the street, you have smooth pursuit of your eyes following that. You're not going to have big saccades. It's going to be a gradual progression. You can move your finger in front of your eyes and kind of slowly track it one way or another. Those are smooth pursuit movements. We also have vergence movements, and this includes both convergence, kind of when the eyes go together to maintain their focus. So when you put that finger, or in this case that pen, in front of his eye, he's got convergence, focusing in on that object. Whereas when he's trying to look at the background, look at the wall behind him, in front of him, that's going to be divergence, and those eye muscles are going to kind of move away. So the further something is away from you, you're using divergence to kind of look far away, where if you're looking at something close, you're going to use convergence. There are all of those kinds of eye movements are movements where both of those eyes are moving together. There's one where the eyes are moving separately, and these aren't as typical, where the eyes don't move together. The other thing that we have going on with eye movements is that our eyes are really good at reacting to changes in our position. So here we see he is moving her head and her eyes don't move. He's told to keep her eyes still, fixating on one point. And so even though he is physically moving her head, those eyes are maintaining their focus, even when the head moves. These really help to stabilize the eyes relative to the external world. And so they're compensating for that movement of the head, so we can really maintain a kind of constant image of whatever it is we're looking at. We also have saccadic suppression, which is why we don't see movement when we move our eyes. So when we move our eyes, we don't see the objects as moving because we have suppression. The visual system shuts down, the retinal input during those eye movements, so that we're not perceiving motion where there is no motion. So the visual system can suppress the images coming onto the retina because they know that the eyes are in movement. So here's an image from your book that talks about how these eye movements really work with either moving objects or stationary objects. So in this first image, the eye is still, but the object is moving. And we perceive that as motion. But we can also perceive motion when the eye is moving, where that image is going to maintain its position kind of on the fovea, where we're tracking something. Smooth pursuit, we're tracking something and we maintain, focus on that object. Or, again, those the reflexes to keep maintaining our focus. So even though the eye may be moving or the head may be moving, that we're still foveating on it. And we perceive this as motion too. And in this image, the second image, there's also a blue object that is stationary. That one does move on the retina because it's not moving. And so this gives us information. Well, we know our eye's moving, and that thing didn't change. It did change places on our retina. So then it is not moving. So again, these are different ways in which we get information about movement based on the movements of our eyes, the position on the retina, the stability of our eyes, and whether it's changing places on the retina or not. One of the ways that we think that this happens, how we're able to integrate this information from our eye muscles with our information that's coming in about movement is the corollary discharge theory. And this really says that the superior colliculus, remember that part? It was, only about 10% of the visual information was going there. But what we think is happening is it's sending information both to the eye to move, but it sends a copy of that information to the motion perception section of the brain so that the brain can compare the two. So the brain knows ahead of time that the eyes are going to move. It doesn't have to wait for the information to come from the optic nerve and from the retina. It got that information ahead of time. And so it'll match those two up. Do they match? Do they not match? And that will give information about movement of objects in our visual field. There's a web demonstration that I have on there, and there's not any participation points assigned to it, but I still definitely suggest that you do it. It really kind of helps walk you through this theory, and your book does a good job discussing it as well. Finally, this information from the CDS, this corollary discharge stimuli or signal, could be more useful than information just from the eye muscle. So if we were just getting information from the eye muscles, we wouldn't get that information until after the effect, after it happened. Where with this CDS, we're getting information about eye movement before the eye even moves. We're getting information about intended eye movement is how your book discusses it. And so we're able to kind of prepare, our brain is able to prepare for that incoming information based on that. Some of the different evidence that we have to support that we really think that this is the theory that's got the most validity is that some visual neurons change their receptive field locations just before an eye movement. So again, it's the idea that we know the eye is going to move, so we better hurry up and get ready for this eye movement. And these visual neurons are responding in a way that suggests that they know what the eye is about to do. CDS would send these signals before the eyes actually move, whereas the signal from the eyes is sent during the movement, and it would arrive at the brain afterwards. But because, again, we're getting both of these, we're able to kind of see, the brain is able to prepare for that incoming information. And we really have support for this theory both primarily from single-cell recordings of monkeys. That again, that they have this idea of intended movement, that the eye is preparing to move, and the neurons are responding that way. There's a figure 717 in your textbook on page 244 that kind of shows you some of this evidence of this support for the CDS. Thanks, and that concludes lecture 3. See you again.